Okay, I guess maybe we can start. So first, some announcements. So I saw all of you have submitted your midterm, and we will grade it. I haven't got the time to grade it. TA will grade it, and maybe we will comment on that later. So we have almost passed half of the quarter, and then we have already finished part 1 and part 2. If you look at the syllabus, I secretly also add part 4 because I don't know. Maybe we'll finish part 3 and then we have nothing to learn. So that's why I add something. But no panic. The final exam will only be covering part 1 and part 2. So part 3 and part 4 will not appear in your final exam. So part 3 and part 4, there's also no homework associated with these 2 parts, no exam associated with 2 parts. I only wish you can learn it, and then there's no further requirement. So don't be panic. And then all we want to exam about is only part 1 and part 2. Okay, so what is part 3 and part 4 about? Part 3 is about quantum statistics. It's about quantum many-body systems, second quantization, those topics. And part 4 is about perturbation theory. The reason that I wish to teach you this is because even if I don't require anything in the exam, but I still wish you can learn, and I want to teach it because when I was a student, like 20 years ago at your age, I was also learning these things, and then I was not very satisfied with what the textbook was written. So basically, I create my own way of understanding it, and then I write it on Wikipedia page. So the Wikipedia page nowadays about these 2 topics was written by me. So that's why I want to teach you. And 20 years has passed, and then it seems that my understanding has been accepted by the community. So it kind of is standard. But it will be a little bit different from what the standard textbook will be about. So okay, now let's start part 3 about quantum statistics. Quantum statistics is a subject about combining quantum mechanics and statistics physics. So statistical physics is talking about how to deal with many-body systems. If you have many particles coming together, you can't keep track of the motion of each particle, so you want to use the principle of statistics to understand the collective behavior of these systems. And then quantum mechanics, as we already know, it's about microscopic particles. So quantum statistics is how to combine statistical physics with quantum mechanics to understand many microscopic particles. So in order to understand that, we first need to understand how do we describe many-body system in quantum mechanics. So that's what I want to talk about first, which I use a slogan called tensors are vectors. The idea will be clear very soon. So to go from single body quantum physics to many body physics, basically we need to, so we start from 1 to 2. Basically what we have learned so far is mostly about single particle physics. We talk about a single, for example, a single harmonic oscillator or a single electron moving around the proton, or maybe a single qubit. But in many cases, we also want to deal with quantum systems which contains many particles. So it's necessary to go from 1 to many. And then last time, I think when we talk about angular momentum, we have learned that you can put 2 spins together and fuse them. So that's already the idea of how to combine 2 single particle states and fuse it into a many-body state. But today we are going to be more systematic, go beyond this spin fusion, and talk about the underlying fundamental principles of how to construct quantum many-body systems out of a single particle system. So as an example, I want to first talk about if I want to combine 2 qubits together. So each qubit, as we already know, has 2 basis states, 0 and 1. They span the 2-dimensional single particle Hilbert space. That's for single qubit. But now, if I have a 2 qubit in my system, then 2 qubit together will have 4 basis states, spanning a 4-dimensional Hilbert space. And we can actually arrange these 4 basis state in a table like this, which is labeled jointly by the state of the first qubit, or qubit A, and the state of the second qubit, or the qubit B. So we basically write the state of the first qubit as the first index, and then the state of the second qubit will label the second index. So in this way, the two-body Hilbert space or the two-qubit Hilbert space will be a four-dimensional space with four basis states. So based on the principle of quantum mechanics, every quantum state of a two-qubit system must necessarily be a superposition of all these four basis states, which can be written as a generic state, as a linear superposition with superposition coefficient size 0, 0, 0, 1, 1, 0, and 1, 1. So these four are complex numbers. And these four numbers, because they are labeled by two indices, alpha and beta, where alpha and beta both goes from 0 to 1, so you can also arrange these four superposition coefficient as a 2x2 array, or you can call it a matrix. Remember that previously we say that every state is described by a vector. But here, sometimes we don't need to stick to that rules. Sometimes this coefficient for many-body systems can also be arranged as a matrix or an even higher order tensor in this case. But however, it makes no difference to rearrange them as a vector. For example, you can just arrange these matrix elements as a column and then call it a column vector, such that the components of the column vector are the corresponding matrix element. So this operation of taking a matrix and convert it into a vector by rearranging its components following the order of, basically following the order that you read a passage, right, from left to right, and then from the first line to the second line, and so on. So following this order, you can arrange higher order tensors onto a vector. This is called flattening. You can flatten a matrix into a vector. Another way of thinking is that instead of this superposition coefficient, which is now labeled by two indices, alpha and beta, we are now using a single integer to label them jointly. And that integer is simply the integer representation of the binary string. You can think of this alpha beta as a binary string, bit string, and then according to the binary number, for example, binary number 1, 1 corresponds to 3. So that's the integer that labels that. But anyway, the idea is that if you have a many-body system, in many cases, your wave function or the superposition coefficient in the state vector will carry multiple indices. And these indices can be flattened. For example, in this example, originally, this is a 2x2 complex number with arranging a 2x2 manner as a matrix. You can also map it to a vector, C4. Which is four complex numbers, okay? But by saying that, we can actually represent any many-body state also as a vector. No need to worry about that they are labeled actually by multiple indices. For example, if we talk about a cat vector 0, 0, it should actually be thought as a tensor product of the 0 state of the A particle and the 0 state of the B particle. That is the joint description of A and B, both in the 0 state. So the 0 state of the A particle has a 1 hot representation. If we assume 0 and 1 are the basis states of a single qubit, then they assume the 1 hot representation 0 should be represented as a 2-component vector with the first component or the 0th component, let's say, being 1. And then this 0 state is the second vector, which also is 1, 0. So the way to represent this combined state as a vector is to first product these two state vectors together as a matrix. You should actually think of it as product it as a matrix and then flatten the matrix into this vector. So the way to do that is to also, by doing these two operations, first product into a matrix and flatten into a vector, this combined operation is called the tensor product. The way to do that is you basically make 2 copies of the second vector and then multiply each copy separately with the component of the first vector such that it spans a larger vector. And you can see, following this principle, we can indeed represent all the basis states in the 2-qubit Hilbert space as these 4-component vectors. I think we have talked about that previously, but I just want to recap. Want to remind you that the general principle to combine 2 subsystems into a larger system is always to take their state vectors and tensor product them together that will form the state of a combined system that describe the state of the 2 subsystems jointly. So tensor product is our tool to combine subsystems. So following this tool, we can now go from 2 to many. Suppose we have n qubits. Altogether, we will have 2 to the power n basis state. Because every qubit can choose to be in the 0 state or 1 state. There are 2 choices. So if n qubits, there will be 2 to the power n choices. And then all these different choices, all these basis states, spans a 2 to the power n dimensional Hilbert space. And each basis state will be labeled by a bit string. Because if you have n qubit, and every qubit assume a state either 0 or 1, then n qubit will be a sequence of 0 and 1s. So that sequence can be written as either as I just denoted as a vector, but actually it's a sequence. And then every component of this sequence is taken assuming value from the set 0 and 1, basically. So the total number of these kind of sequences is 2 to the power n. So by writing that the joint many-body state, we can basically use this sequence to label a many-body state. But when we label the many-body state in that way, what we mean actually is we are basically tensor producting every single particle state together. So the sequence contains, means the first particle is in alpha 1 state. The second particle is in the state labeled by alpha 2, and so on. So you basically take the first state vector, alpha 1 and alpha 2, and so on, and tensor product together. This will form a very large vector, and the length of the vector, or the components of the vector, is indeed 2 to the power n. So this it precisely describes that this state vector is indeed a vector in this 2 to the power n dimensional Hilbert space. But this only describes the basis vector. It hasn't described the generic n-qubit state yet. So a generic n-qubit state in such a large Hilbert space dimension for this multi-qubit system will be a linear combination of all the possible bases, where the bases will be labeled by this bit string or this sequence. And then you need to sum over all the possible sequence. There are 2 to the power n of them. And then you need to combine all the bases with the coefficient, superposition coefficient. These superposition coefficient, because they are jointly labeled by all the sequence, and then every token, every position of the sequence can take 0 or 1. So it looks like a 2 by 2 by 2 by 2 all the way n time. So there are n of them. So 2 to the power n, let's say, tensor. So you have many indices labeling this coefficient. So this big tensor can also be flattened as a C2 to the power n, meaning that altogether you just have 2 to the power n complex numbers. So they form these vectors as well. So all this discussion is trying to get you familiar with the language of tensor product and to understand the idea of, in a many-body system, the wave function or the state vector, the superposition coefficient basically is generically a tensor, but it's also fine to represent it as a vector. So we are still within the framework of the idea that every quantum state is described by a vector. It's just a super big vector. Okay, so in this sense, in conclusion, tensors are also vectors. Many-body states can either be described by tensors like these coefficients, or directly by a cat vector as well, with the predefined tensor structure. It's very important to notice that the basis state can be decomposed into the tensor product of subvectors. It is not generally the case, because in many cases, for example, if you take a superposition of this basis state, this vector will no longer be able to be decomposed into tensor product of each vector in the subsystem. So only the basis state has this very nice, I shouldn't say only, I should say at least the basis state has this very nice property, but that's not general. So when you encounter a many-body state that cannot be written as tensor product of subsystems, that's when we say that the state describes a quantum system that has quantum entanglement. So the concept of quantum entanglement means that it is a quantum many-body state that cannot be written as an individual state, tensor product together. Because individual state tensor products together is like you can specify what is the state of the first particle, what is the state of second particle individually as if they are independent. But in many cases, in quantum mechanics, the interesting thing happens when there's quantum entanglement where the particles are not independent, but they are correlated in some sense. But we will not talk about quantum entanglement further. I just want to mention that the fundamental principle to construct many-body system is to understand the basis of a many-body Hilbert space is constructed by tensor product. And once we know what are the bases of the Hilbert space, we know how to construct the states, which is a superposition of bases. We also can define operators in many-body states, which tells you how to transform one basis state to other basis states. Okay, so with that basic understanding, any questions actually? Yeah. So we want to dive deeper into quantum many-body states. So quantum many-body state describe a quantum system of many entities or many particles. And then actually it splits into two classes. It depends on whether these particles are distinguishable or non-distinct or identical, basically. So for distinct particles, such as spins and qubits, what do we mean by distinct? Because, for example, if you have two spins, you can label them. This is the first spin, this is the second spin, because I'm holding the spins in my hand, and then I have a left hand and right hand. I can distinguish them. But in some cases, there are particles which cannot be distinguished. For example, the bosons. Bosons are emergent particles from harmonic oscillator that we learned previously that was used to describe excitations of these oscillators. And then bosons are not indistinguishable because they just correspond to the energy unit you put into the system. So you cannot say what's the first boson, what's the second boson, because if the system gets excited by two bosons, then there's really no way to tell which boson is the first. So that's why there are also cases where in quantum mechanics particles can be indistinguishable, which is called identical particles. Examples are like bosons and fermions. And the goal of this today's lecture is to understand what is the difference between distinguished particles and identical particles and what is special about identical particles. So in order to understand the difference and similarity, we need to first start from maybe distinct particles. And a distinct particle, the principle is exactly the same as what we just said. So distinct particles are basically the simpler case, which I just repeat everything again, which is distinct particles are labeled by basically the particle themselves can be labeled. So we can specify the state for each particle separately. For example, we can say that the ith particle is in the alpha I state. So for that reason, if each single particle has a d-dimensional Hilbert space such that its single particle basis state is labeled by this alpha that goes from 1 to d, then the many-body Hilbert space of undistinguished distinct particles will be d to the power n dimensional, and then the basis state will be, again, labeled by the tensor product. It's the same principle. I'm just generalizing what I said previously from a qubit to a d-dimensional Hilbert space. I'm just replacing this d equals 2 to generic d. So for distinct particles, you can really tell what is the state of each particle, what's the first particle state, second particle state. And for that reason, it makes sense to write down a many-body basis like that. And for that reason, you can immediately write down the many-body wave function as a superposition of all the basis states, and then you can also find probability distributions. So this state vector basically tells you, for example, if I start from a many-body state like that, I want to know what is the probability to find the many-body system in a specific state alpha, given that the many-body system has already been prepared in such a superposition state. Then according to the Born's rule, the principle of quantum mechanics, the probability to see alpha state conditional on the state system being prepared inside is given by the inner product or the scalar product of alpha and psi norm squared. And then that basically corresponds to, because this basically pick out the coefficient, a superposition coefficient, and then it's the wave function or the coefficient norm square. So that's the probability distribution. So far, so good. So we have established everything as we talked about previously. In single particle quantum mechanics, we can, of course, further define operators on these states. So that's the idea. But when we come to the identical particles, we need to be more careful. Because identical particles does not admit a labeling. You can't label these particles. You can't talk about what is the first particle, what is the second particle. And for that reason, suppose we have a system of two particles, and then the following two descriptions or the two states are indistinguishable. Because, for example, the first state, which is written as alpha 1 tensor alpha 2. So by writing a state like this, we mean that the first particle is in the alpha 1 state, and the second particle is in the alpha 2 state. And then by writing a state like that, we mean that the first particle instead is now in the alpha 2 state, but the second particle gets put into the alpha 1 state. But if we can't really tell who is the first particle, who is the second particle, then this doesn't make sense. There's no difference between these two different states. Although we are writing these two states in different ways, and actually, if these two states, if you write it as state vector, they correspond to actually different vectors. So it seems that we are using different vectors to labeling the same state, and then that creates ambiguity. So that's the subtlety here. For identical particle, because of this indistinguishability, that these two seemingly different states with completely different state vectors actually describe the same state. So this basically means that it will be equally likely to observe the system in this alpha 1, alpha 2 state, which is the first one, as in alpha 2, alpha 1 state, which is the second one. Meaning that if you take the many-body state wave function, so although these two has some ambiguity, you can still anyway represent the many-body wave function as a superposition of these states. But now there's an additional condition that need to be imposed to these many-body state vector. Because previously, we write down this state vector. It is like an arbitrary linear superposition of all the possible basis states. But now, we require that it should be, the superposition coefficient should be such that its component on alpha 1, alpha 2, and its component on alpha 2, alpha 1 should have the same norm square, should have the same absolute value, basically. Because the probability to observe these both cases, because particles are indistinguishable, should be the same. Otherwise, you can tell which one is the first particle, right? So that's the basic principle. So how do we realize a system or a wave function whose probability distribution on alpha 1, alpha 2, and on alpha 2, alpha 1 are the same? The idea is to introduce a permutation operator, because as we can see, what we are doing up there is basically we are saying if you are exchanging the two indices, you should think alpha 1 and alpha 2 as indices or basis states that labels these many-body states. And then if you are exchanging the basis, or if you are exchanging the indices, the wave amplitude or the wave vector amplitude should have the same norm. So in order to exchange these bases, we need to introduce an operator. So this is the first time we introduce an operator in the many-body Hilbert space. And this operator is called permutation operator. And this operator should be considered as a huge matrix. And this matrix is actually 2 to the power d. D to the power n times d to the power m matrix. So this operator is a matrix. It's a very large matrix in the many-body Hilbert space. What the x is, when the x on a basis state, which is labeled by a sequence called alpha, it basically transforms it into a new basis state, which is alpha with a subscript pi. This pi is an element in the permutation group. So permutation group of order n, it means all the possible permutations that exchange or interchange or permute n indices, n integers to each other. So when we talk about alpha with a subscription pi, we basically mean that it is the same sequence of alpha, but permute by this pi. Meaning that the original sequence, for example, is alpha 1, alpha 2, alpha n, which means that the first particle is in the alpha 1 state, second particle is alpha 2 state. Then after permutation, the first particle will be pi acting on 1, meaning that pi is a mapping that will map 1 to something else, and then the first particle will be in a different state. But sometimes pi can also map 1 to itself, but in general, it will be a different state. Maybe this is too abstract. Let's look at a very concrete example. Suppose we are talking about 3 particles, then this n is 3. So a permutation, for example, in S3, basically corresponds to a bijective or invertible map from 3 objects to themselves. For example, we have 3 objects, which is called 1 and 2 and 3. We just use integers to label these 3 objects. Under permutation, for example, one possibility is that you can exchange the second and the third object such that 1, 2, 3 under the permutation becomes 1, 3, 2. So 1 gets mapped to 1. This object doesn't get permuted, but 2 and 3 interchange. So 2 goes to 3 and 3 goes to 2. So this is what we mean by permutation. So when we say pi acting on 1, we basically means that the mapping result of this permutation acting on the index 1. For example, in this case, pi 1 is 1. But pi 2 is not 2. Pi 2 is actually 3, because 2 gets mapped to 3 under this permutation. So this, by saying that there is a permutation in S3, we basically mean that this permutation is fully described by the following mappings. Mapping is like a function, which takes in an integer and output another integer. So it has integer input, integer output. And then this mapping is bijective, meaning that every integer gets mapped to a distinct integer. Different integers maps to different integers. The same integer maps to the same integer. That's the idea. So that is what we mean by a permutation. So for any permutation, you can use the permutation to generate a new sequence given the original sequence. For example, if I have an original sequence alpha, which is alpha 1, alpha 2, alpha 3. So these 1, 2, 3s are the indices of this sequence. But this alpha 1 itself is also an integer. Alpha 1 itself is an integer which takes value. Every alpha I is an integer that takes value from 1, 2, and so on to d. Okay, so that's different. Okay, so this alpha has d. Basically, you have d number of choices for this alpha if the single particle Hilbert space dimension is d. So you should think that it's a sequence, and then under the permutation, what happens if you just need to for the second alpha, because 2 gets replaced by 3, so alpha 3 comes to here, and then 3 replaced by 2, so alpha 2 goes to here. So this alpha pi basically corresponds to a new sequence, which corresponds to the permutation acting on the original sequence. The simplest way of thinking it is if this permutation exchange 2 and 3, then basically you need to exchange the indices that was labeled by 2 and 3 here into the new sequence. Okay, so the permutation operator in this sense is easy to understand, that the permutation operator is specified by a permutation which is described by this mapping pi. Pi is the mapping that specifies the permutation. Permutation operator, as an operator in the quantum mechanics, it must act on a basis state and give you another basis state. And what it does is acts on the alpha state and give you alpha pi. And then this is the description of this operator. So this operator itself is not directly the mapping, but it is an operator associated with this mapping. And then that allows you to convert this state vector to a new state vector. And this operator actually implements the permutation of particles. Is that okay? So that's what I want to talk about permutation operator. Then with this understanding, we can actually specify what are the conditions for these state vector many-body states if we require that the state has some property under permutation. So by saying that their identical particles cannot be distinguished, that means there's a permutation symmetry that is imposed to the probability distribution. For example, if I have a many-body states of identical particles, no matter what the state is, then it necessarily must satisfy the following condition, that for any permutation in this n-particle space, that means this alpha is a sequence of length n. And then for this length n sequence, and I can arbitrarily permute its tokens, its elements, basically. And then it will end up with, there are n-factorial different ways of permuting that. So this, although you can see this is an equality, it's actually many, many equalities. It's n-factorial equalities, it's many conditions. So no matter how you permute this alpha, these all possible permutations end up with different sequence, they all have the same probability to be observed given the many-body state, because otherwise the particle will be distinguishable. If the particle is indistinguishable, there should be no way to tell which is the first one, which is the second one, so they should be all on equal footing, and then their probability distribution should all be the same no matter how you permute the label of the state of the particle. So that's the idea, that's the principle of what we mean by identical particles and identical system, many-body systems of identical particles. But this equality of probability distribution simply translates into this equality that is imposed on the superposition coefficient of the state vector. Because the state vector, the many-body state, is anyway just a linear superposition of all the alpha bases. And then the superposition coefficient is psi alpha. So this probability being equal, meaning that psi alpha, this component, must be the same as psi alpha pi, another component whose index was related to the previous one by permutation. And although they at the wave amplitude level, they don't need to be the same, but if they take an absolute value and square it, they need to be the same. So if you have two complex numbers, they are the same under absolute value square, then you know that these two complex numbers can only be related by an overall phase factor, meaning that psi of alpha can only be related to psi of alpha pi by some overall factor. And this overall factor may depend on what kind of permutation you are doing. So what does this mean? This basically means that this alpha as a wave function or a state vector, it realizes a one-dimensional representation of permutation group, meaning that for any permutation group element, it will correspond to a complex phase factor that multiply on the many-body wave function. And then mathematical fact is that there's only two one-dimensional representation of any permutation group. And one is called a symmetric representation, the other is anti-symmetric representation. Maybe this is too abstract, but the idea is that if you think about permutation, all possible permutation is made of exchange. Exchange is the fundamental building block of permutation. Exchange corresponds to you have a sequence, you only take two of them and then exchange their places. Any complicated permutation can be built up from just keep doing exchange. You exchange enough many times and then you can realize all possible permutation. So only thing we need to specify is under exchange, what kind of phase factor we need to accumulate. So suppose under exchange we can accumulate a phase factor. You know that there's no arbitrary choice. This phase factor can only either be 1 or -1. The reason is that exchange is a twofold operation. If you exchange and exchange, then you are coming back to the original sequence, right? You are not doing anything. So if you exchange and accumulate a phase, and exchange again, accumulate another phase, the two phase factor will multiply together and become the square of the phase factor, which must be 1, because if you exchange twice, you are doing nothing. And then the only complex number that can square to 1, there are only two complex numbers, only two real numbers actually, +1 and -1. So there are only two possibilities. Either when you exchange, you get nothing, you do +1, meaning that no matter how you exchange, the wave function, if under exchange, is still the same. That is the first case. And this case is called the symmetric representation. And any many-body system whose wave function satisfies this condition is called a bosonic system. And the particles that form these many-body systems are called bosons. And then there's another solution where every time when you exchange, you get a minus sign. So if every time you exchange, you get a minus sign, then if you do a generic permutation, a permutation is just combination of exchange, then there's a permutation sign associated with each permutation. The permutation sign is defined to be such that it is +1 if this permutation contains even number of exchanges. It is -1 if it contains odd number of exchanges. This is precisely the principle that every time when we exchange, if we get a minus sign, then if we exchange 3 times, we still get a minus sign. If we exchange 4 times, we get a plus sign. So that's why this is a this is a sign associated with each permutation. You can show that every permutation can be decomposed into exchange, although every permutation has multiple ways to be decomposed into the exchange. But the number of exchange, the parity of the exchange, meaning that whether the number of exchange is odd or even, actually doesn't matter. It doesn't depend on the way that you decompose this permutation into exchanges. For example, if you take S3 group, which correspond to the threefold permutation, which means it's a permutation that takes 1, 2, 3 to any other possible combinations. So 1, 2, 3 can either go to 1, 2, 3. You can see in that case, there's no exchange. When there's no exchange, then this is an identity map, then it is +1. Or if you go to 2, 3, 1, you can show that it's actually 2 exchange, because I can permute 1, 2, 3 to 2, 3, 1 by taking 1 over 2 and taking 1 over 3 again. So I drag this 1, commute through 2, commute through 3. So I need 2 exchanges in order to push this 1 from the first places to the last places. And because of these 2 exchanges, I will have a +1 because the number of exchange is even. And then there are also cases where the number of exchange is odd. For example, the last case where I'm switching 2 and 3, which is a single exchange, so I get a -1. So this is the rule of this permutation sign. And this permutation sign is just a way to represent that every time you exchange, you get a -1. So if your many-body wave function or this state vector components satisfy this equation, then the corresponding many-body system is a fermionic system, and the particles in this system is called a fermion. And this representation is also mathematically called antisymmetric or sign representation of a permutation group. So based on these mathematical principles, we start from the very general principle. We assume that there is a many-body system where the particles are identical. Based on that assumption, we establish the fact that in that case, the state vector component must be related by this relation, and this relation only allows you to attach an additional sign to these wave functions under the permutation operation. And then there are only 2 possibilities to attach these signs consistently, which is symmetric or antisymmetric. So in our universe, there are only 2 types of identical particles. One is called boson, where under exchange, the wave function doesn't change sign. The other is called fermions. Under exchange, the wave function changes sign. So you can see there's no way to distinguish a single particle, to assign to a single particle whether it's boson or fermion, because a single particle has nobody to exchange with. So, so this boson and fermion, this notation, or the distinction of boson and fermion is only there in a many-body system. Only if you have more than 1 particle, you can tell whether the particle is boson or fermion. If you just have 1 particle, there's no way it doesn't make sense. There's no well-defined notion of boson and fermion. So boson and fermion, these distinctions only arise in many-body systems. That's all the possibility that we have in our universe. That's the 2 types of particles. And that's indeed the case in the standard model. So we know that our universe is made of all these fundamental particles. And then there are particles like electrons or neutrinos or quarks. Quarks actually are the particles that are made of the nucleus. And then these particles, electrons, neutrinos, and quarks, they are called a matter particle, because these particles are the particles that are made of the matter. And then these matter particles turns out to be all fermions. They are all fermions. And then there are also other particles, which like photons, which is the quanta of light, which also have like a W and Z bosons, which is the boson that mediates. I already called them boson. So photon, WZ boson, or these gluons, they are all bosons. They mediate electromagnetic interaction, or mediate weak interaction, or mediate strong interaction. These particles are all force-mediating particles. These particles mediate the force between matter particles. So our universe is organized in a very interesting way, that all the matter particles are fermions, and all the force mediators that that is like a messenger that carry information between the matter particles. They are all bosons. And there's also a very interesting boson, which is called the Higgs boson, which is the boson that give rise to mass for all the particles. And then that turns out to be also a boson. And it's actually very important that the Higgs boson is a boson. If the Higgs particle is a fermion, actually one can derive that all the particles will have no mass. It's impossible to have mass for every particle. So the fact that every particle has a mass actually indicates that the Higgs particle is a boson, but that's too far. I just want to say that even if you look down into the fundamental particles of our universe, it couldn't evade the derivation that we have today, that all the particles are classified into boson and fermion. And the fundamental difference is in their many-body wave function. Boson exchange is symmetric, and fermion under exchange is anti-symmetric. Okay? So that is the boson and fermion state, the principle of boson and fermions I want to talk about. So now let's look a bit more carefully about how to construct these many-body states, because we are only saying previously we didn't give an explicit construction of this psi. We are just saying if the psi satisfies this condition, if psi satisfies the other condition. But how to write down this psi? How to write down this psi in a way that it automatically satisfies this condition to be a bosonic wave function, and how to write down in a way that it automatically satisfies this condition to be a fermionic wave function. Because we know that if you arbitrarily assign a complex number to these state vector components, you're not going to satisfy this condition automatically. So now I'm going to discuss how to assign these wave vector components in order to make this symmetric or anti-symmetric property explicit and built-in and automatic. So the way to do that is called the symmetrization. So you can always take a state which does not satisfy this symmetry condition, and you perform symmetry transformations on the states, and then summing over all the possible symmetry transformation outcomes. It is like, for example, if this guy, this stick is not symmetric under rotation, right? So what I can do to symmetrize it is I take this configuration and rotate by an angle, rotate by an angle. I just keep performing symmetry transformation to this object, and I summing over all the possible symmetry transformation of this object, like averaging over it. Then it will become a disk, basically, and then it will become rotational symmetric. So the very simple idea of summing over all symmetry operations for bosonic system is simply called the symmetrization. So for any state, alpha, this alpha may not be symmetric under permutation because alpha is a state that is labeled by a sequence, right? This sequence contains alpha 1, alpha 2, alpha 3. They are not the same. So if you permute alpha 1 with alpha 2, maybe you end up with a different sequence that is a different state. But no worry, don't worry about that. Take this state and apply an operator which is called the symmetrization operator on the state. The symmetrization operator will automatically symmetrize the state such that the state basis now will be invariant under the permutation, which is actually what we required. So the way to do that, the symmetrization operator, what it does is basically it apply the permutation operator to the state and then summing over all the possible permutations that you can possibly perform for an n-particle system, and then you are summing over all these permutation outcomes. So another way of writing it is that if you give me any alpha, I can enumerate all the possible new sequences, which is labeled by alpha pi, which is related to the original sequence alpha by the permutation pi, where pi is summing over all the possible permutations. So there are n factorial number of possibilities here, and if you sum over them, and then you will obtain a basis state. So I'm not talking about the wave function yet. I'm talking about the basis state. You can construct a basis which is symmetric under permutation. Following the same principle, you can also do this exercise and construct a basis that is anti-symmetric under permutation. What we do is that every time when we permute, we attach a -1 to the pi, a permutation sign to that, such that such that this new basis state will be anti-symmetric under permutation. Maybe this is a bit abstract, so let's look at examples. Examples is a two-particle system where n equals 2. We'll only have two particles. If we only have two particles, then this alpha is labeled by a length 2 sequence. Maybe I call it, instead of alpha 1 and alpha 2, I will call it alpha and beta. Suppose I have a two-particle system where the first particle is in the alpha state and the second particle is in the beta state. This state itself definitely is not symmetric, because if I exchange alpha and beta, it becomes beta-alpha state. Beta-alpha state is not the same state as alpha-beta. But it's not a problem. We can symmetrize this state. By symmetrization, I can apply the symmetrization operator on the state. What it does is first is enumerate all the possible permutations in the two-particle permutation group, right? The two-particle permutation group only has two group elements. One is identity, do nothing. The other is exchange. So either you do nothing, then the state gets copied here, or you exchange the label between them, that is implementing a non-trivial permutation, actually exchange. In this case, that goes to beta alpha. And now you sum them over. Once you sum over, you end up with a state like that. The basis state like that is actually a symmetric basis, because in that case, now if you try to permute the two labels, then this alpha beta plus beta alpha state, under permutation, you will go to beta alpha plus alpha beta. But what's the difference between alpha beta plus beta alpha and beta alpha plus alpha beta, right? We know summation, you can interchange the two state vector before and after summation. So this summation automatically resolve these non-symmetric cases for these indices. So it automatically gives you a basis state which is automatically symmetric under permutation. For example, you have alpha alpha. In that case, the basis state is already symmetric. Then if you try to symmetrize it, maybe there's a factor 2 here, but that's not important because the basis can always be normalized later. So under the symmetric operation, then it's alpha alpha plus alpha alpha, basically, and then that is still alpha alpha. And what about alpha beta? If you try to anti-symmetrize, then it goes to alpha beta minus beta alpha. And then this is a basis that is automatically anti-symmetric under permutation, because now if you try to permute the first and second particle, then this state goes to beta alpha minus alpha beta. But that state is just a minus sign of this state, right? So that automatically realizes the case that when you exchange the two particles, there's a minus sign. But if you try to apply the anti-symmetric operation on the alpha alpha state, you will see that the result is alpha alpha minus alpha alpha. Then that's a non-trivial case where the resulting state is simply 0. That means there's no such basis state in a fermionic system that has two fermions occupying the same state, because this state was supposed to mean that the first particle is in alpha state, the second particle is also in the alpha state. But it's not possible to have such a state in a fermionic system, and that actually is obvious, or that's self-evident by the fact that if you apply the anti-symmetric operation to the state, which in order to construct the fermion basis, you will find that this kind of construction automatically fails for you. This construction will lead to a 0 state. That means there's no such a basis, and that's why there's a Pauli exclusion principle, that there can be no two or more identical fermions cannot occupy the same state simultaneously. So you can see it's very powerful to use these symmetrization and anti-symmetrization operation to construct basis state, which is automatically bosonic or fermionic. And then the terrible-looking formula above is simply a generalization of these cases in an n-particle system when n is greater than 2, let's say. But for two-particle system, we can already count how many states are there in the Hilbert space. For a two-particle system, if I consider a 2-qubit system, so if I consider 2-qubit, then basically this alpha and beta can take value between 0 and 1. So for the symmetric state, we have 0, 0 state is symmetric. 1, 1 state is also symmetric. 0, 1 plus 1, 0 state is also symmetric. So there are 3 symmetric states, and there's one anti-symmetric state, which is 0, 1 minus 1, 0. So that's indeed the spin triplet state, which is symmetric, and the spin singlet state, which is anti-symmetric for a 2-qubit system. So if you have 2 qubits, that's bosonic, that has 3 states, and if it is fermionic, that has 1 state. And they add up into the 4 total number of states in a 2-qubit system. However, this is not always the case. So maybe I will talk about it more next time. But if you really count how many bosonic states are there in a many-body system, or how many fermionic states are there in a many-body system, there's some counting which I don't want to go through. Eventually you will find the number of bosonic states and the number of fermionic states add up together. Most of the case doesn't saturate the full total number of states. So that means there's some state in the many-body Hilbert space which is neither boson nor fermion. So we would deal with this subtlety maybe next time. Thank you. Yeah.